Welcome to this presentation about strong typing for Excel from Lyquidity. The objective of this presentation is to show how strong typing can be used to help you create more robust spreadsheet models. I will begin with a review of some of the findings about the extent of errors in spreadsheets, before talking about some useful approaches taken by the programming community to combat errors in conventional programs. Finally, I will provide the information you need to take the next step, and begin using strong typing. I will not demonstrate strong typing as part of this presentation, but please visit our website to see the software in action. The videos show how strong typing allows a user to apply some of these programming ideas to reduce the incidence of unforced errors when creating spreadsheet models. So let's talk a little about errors in spreadsheets. That errors exist in spreadsheets is nothing new, as this summary of past investigations by a range of organizations shows. What is surprising is that error rates are so high and that, over a 10-year period, there was no apparent reduction of the incidence of errors. The most recent of these figures are now 10 years old. Perhaps it is a testimony to this persistence that there are no more recent reports of audits results. Ray Panko suggests that the existence and prevalence of errors in almost all spreadsheets should come as no surprise, because it is a reflection of the rates of errors found in other, comparable, human activities. However, if the existence of errors in spreadsheets should come as no surprise, then, perhaps, that error detection rates are also very low, should be a surprise. While intuitively one might expect expert spreadsheet users to find most errors, studies have found that even experts detect barely more than half the errors, and this when looking for them purposefully under the watchful eyes of a researcher. Again, this is consistent with research in other fields. Such research shows there will be an error in every 20 complex logical activities. Powell, Baker and Lawson attempted to classify the types of error that appear in spreadsheets. You can see from the table that only about 25% of the errors introduced are there because of faulty logic. The implication is that some 75% of the errors exist because of more mechanical problems. These types of errors are amenable to detection if only the appropriate information is available to the spreadsheet engine. Ray Panko concludes that a way to reduce the incidence of mechanical errors, such as the use of invalid cell references, or hard-coded values, and even to highlight where some of the logic errors may be occurring, is to employ techniques from traditional programming disciplines. We agree. Our business is creating software using programming disciplines. In strong typing, we've leveraged our knowledge of programming and our experience with Excel to create a tool which will help experienced Excel users create spreadsheet models with far fewer unknown errors. It's worth saying that strong typing is not a replacement for existing auditing and model creation techniques. Good spreadsheet development practices such as planning, documentation, testing, as well as separation of input, logic and presentation, are all valid techniques and used extensively when developing software products. For example, a heavily used architectural paradigm for creating software programs is Model View Controller, or MVC. An MVC architecture separates concerns across data, which is represented by the model, across presentation, which is represented by the view, and logic, the controller. This separation is what good Excel users do anyway. So what if the model author is able to more easily identify the 75% of errors, and so spend more time focused on ensuring the logic of the model is correct? That's the purpose of strong typing. Strong typing is an add-in for Excel that allows spreadsheet model creators to add metadata to Excel, metadata that strong typing can use to validate model formulas. In this presentation I will review what types are, and why they are a benefit to programming projects, what scopes are, and why they make validation more flexible, and how assertions can be used to implement specific validations. I will also review how these metadata, types, scopes and assertions, can be assigned to cells and cell references within formulas, so that StrongTyping is able to perform extensive formula validation. The purpose of using StrongTyping to add metadata is to identify and display errors, and also potential errors in the formulas that together are the spreadsheet model. That is, the purpose is to get to the point illustrated in this screenshot. There are many different programming languages. These languages can be categorized in different ways, such as whether they are imperative or declarative, functional or non-functional, general or domain-specific. For the purposes of this presentation, another useful categorization is whether the language is dynamic or statically typed. Common examples of dynamic languages include JavaScript and PHP. Most web pages contain some JavaScript, while PHP is used to create the popular blog software, WordPress. Common examples of statically typed languages are C, C++, Java and C#. Any operating system you care to think about has been developed using C or C++. Meanwhile, Android is a mobile Java application. Dynamic languages are considered, in quotes, easy to use, because they don't require the programmer to define more types than the small number of built-in ones provided by the language, such as number, string and boolean. They also coerce values from one type to another. If the program is asked to add a piece of text containing the digits 1 and 2 to the number 8, it will coerce the text to the number 12 and then add it to the number 8 to yield a result of 20. Dodging the need to add types sounds like a great way to go, but the result is usually error-prone code. For this reason, it is uncommon for significant programming projects to depend upon a dynamic language if there is an alternative. Where a dynamic language cannot be avoided, there are often tools to retrofit a type system. For example, eBay, which must rely on JavaScript because it is the only practical choice for browser-based applications, created VJet, so their programmers could write JavaScript, but in a way that allows them to include type information. Microsoft has recently released a tool called TypeScript. This is another tool to allow JavaScript to be written in a way that can include type information. Excel's formula syntax can be characterized as a dynamic, domain-specific, functional language. Like other dynamic languages, it supports only a small set of native types. Maybe then, it is not surprising that, like other dynamic languages, the results of its use are often error-prone. By contrast, major software projects use statically typed languages, whether it's an operating system, a web server, your mobile phone or the Microsoft Office suite components. The benefit of using a type system will be reviewed in the next few slides. So what is a type? And what is it good for? Dynamic programming languages are more natural to use, because it is unusual for people to consciously think about types, even though we use them all the time. This presentation is prepared without a type system. But as a consequence, there is nothing but my good sense from stopping me quoting Shakespeare, or reciting a limerick. Types are names used to identify things, so generally they are nouns. The compiler for a programming language, which supports a type system, is able to use this additional metadata to ensure the programmer does not confuse apples and oranges, or chalk and cheese, unless that's what's really required. The name of a type can be anything. The compiler for a programming language doesn't care, because to it the type name is just a sequence of bits. So usually a type name is a name which will allow the programmer to recognize what thing is being used in a program and allow the programming language tools to highlight potential or actual errors. Here are two examples to illustrate why types can help a programmer to identify an error. Let's start with a JavaScript example. In the example, Two variables are declared and they will be used to hold the number of oranges and the number of apples respectively. The var keyword is the instruction to JavaScript to allocate space to hold a value. In Excel these would be, say, the cells A1 and A2. Because JavaScript does not use a type system, beyond the rudimentary value types of number, a string of characters and Boolean, the addition of apples and oranges is okay. Like an Excel formula, a JavaScript program cannot be provided with additional information that the language can use to confirm this addition is appropriate. The second example uses C#. C# is statically typed so does support a type system. The syntax of this language is similar to Java. The difference between this example and the JavaScript one is that two types have been defined. One called apples, the other called oranges. This time, when the variables are declared, it is done so using the new types, but in all other respects this code is the same as used in the JavaScript example. However, you can see that because types have been defined and used, it's possible for the programming language tools to let the programmer know what's been coded is not valid. Wouldn't it be good if Excel cells and cell references within formulas could be augmented to include additional information that can be used to highlight potential and actual formula errors? Detecting and highlighting issues using types is important, but it's also necessary to allow types to be aggregated in some way. For example, gross profit is the difference between revenues and cost of goods sold, so it must be possible to express that relationship while also detecting the inclusion of incorrect accounts if any are included. Continuing the example, if it should be possible for the number of items in a basket of fruit to be counted, then a way to accommodate this is made possible because types are organized hierarchically. Okay, for the horticulturalists, we know apples are not citrus fruit. Apples and oranges share a common clade, but we hope that in the interests of the clarity of the example, you will forgive us taking liberties with the taxonomic labels. So, with this excuse, here it is made explicit that both apples and oranges are descendant types of the more generic type citrus fruit, which in turn is a descendant of the most generic type, fruit. In turn there may be subtypes of both apples and oranges. As a result, it requires only a simple change to the code so that the total variable is defined to use type citrus fruit instead of apples. Likewise, it is then an error to add bananas to a basket of citrus fruits. But that issue can be resolved by making the basket a basket of type, fruit. StrongTyping is an add-in to Excel which is presented as a custom task pane, controlled from a new tab added to the Office ribbon. We will be working with StrongTyping shortly, but I want to relate the comments about the ideas borrowed from a statically typed programming language's type system, to Excel. To illustrate this relation, I will begin by using a very simple spreadsheet. You can see the selected cell is C7, which holds a computed value for gross profit. The formula in this cell is exploded and shown in a graph format in the task pane on the right. The display in the task pane on the right-hand side shows lots of information about the formula, about the types defined so far, and about the types assigned to components of the formula. The lower portion of the task pane displays the types defined so far. The checked types are the ones assigned to the currently selected node of the formula graph, the reference to the cell at C6. Each component of the formula is shown as a node in the graph. It is this graph which is shown in the top part of the task pane. The cell result, and each node that represents a cell reference in the formula, is assigned a type. You can see that the cell result has been assigned a type named gross profit. The cell at C5 is expected to have been assigned a type of sales revenue, while the cell at C6 is expected to have been assigned a type named either COGS1 named COS. In this example, the formula has been validated. The references in the formula are correct. That is, they refer to cells that have been assigned the appropriate type. Cost of goods sold and cost of sales are the same in this example. But really only one is required. However, it is useful to show that a cell reference can be assigned more than one type. This happens often when the formula is a sum function, or any function that takes a cell range as an argument, when the objective is to validate that the cells in the range being summed are only of specific types. For example, it would be inappropriate for gross profit calculation to include the value of retained earnings. Let's go back to ideas from the programming domain to look at the idea of scopes. The idea of a scope is straightforward, and reflects its dictionary definition. So it's in this sense they are familiar. When a cell reference is used in a spreadsheet formula, the scope is the whole sheet of the cell in which the formula exists. That is, the reference A1 means the cell A1 in the same sheet. If the reference should be to a cell in a different sheet, then a sheet name must be included in the cell reference. From a cell reference validation point of view, this is a pretty wide scope. What if the validation should ensure that the cell reference refers to a cell in the same column or row, or to an adjacent column or row? In traditional programming, the idea of scope is about when variables can, and cannot, be accessed. There is a rough analogy between a variable in a program, and a cell in a spreadsheet. Both are used to hold a value. So a scope is an important tool to help ensure a program only accesses a variable when it is valid, that is, in scope. The scope of a program created using VBA is the function, or sub. A variable declared in a VBA program function or sub can be accessed anywhere in that function or sub. In other languages, scope is defined using delimiters, one that marks the beginning of a scope, and another to mark the end. In the case of JavaScript, C, Java, etc., the delimiters are curly braces. Using this mechanism, languages offer the programmer an arbitrary number of scopes within a function. This is useful because errors occur when variables are used that are uninitialized or contain invalid data. When used in StrongTyping, scopes provide more specific validations. Scopes are assigned to cells to create logical groups. A scope could be used to identify the group of cells that contain actual data, or the data for a specific period, or which represent balance sheet or income statement data. There are no predefined scopes, and scopes have no inherent meaning. Any scope created means only what you want it to mean. The cells belonging to a scope do not need to be contiguous. A scope might define the cells that contain debit or credit values, or be data input cells. The reason to define scopes is so that cell references can be checked to ensure cell references refer to valid cells, and in this way allow greater assurance over cell reference sources. The last idea borrowed from programming is the use of assertions. In programming, assertions are commonly used to test the validity of arguments passed to a function, or to perform a reality check on the results of a computation. Typically they will output an error, or warning message if the assertion fails. In StrongTyping there are many assertions built in, and these can be used to fine-tune formula validation. For example, it may be essential to confirm the source of a cell reference is not blank, or is numeric, or in the same column. Referenced cell values can check to confirm they are in a range of cells, or take one of a set of discrete values. The metadata, that is the types, scopes, assertions along with details of their assignments are stored within the workbook document. This means the metadata is copied with the workbook document whenever a copy is made, or a copy is sent to colleagues for change and review. The metadata will not be removed by someone who does not have the add-in installed, and the metadata will not be removed through the normal use of Excel. However, because the metadata is in the workbook, it can be removed by someone hacking the document file. If a colleague makes a change to the workbook, any issues with the changes can be reported when the document is returned to you. New formulas and cells will appear as warnings, while changes that adversely affect the validity of the model will be reported as errors. The existence of StrongTyping metadata does not affect the operation of the workbook. StrongTyping provides facilities to promote the reuse of metadata. Each time a workbook is saved, and if there have been metadata changes, then there will be a new version of the metadata created. Versions can be selected, named and deleted. Any one of the versions can be exported to a file which can be imported subsequently. Alternatively, it is possible to create templates from the current version. The metadata exported can be just the types, scopes and assertion definitions, or it can also include the metadata assigned to cells and formulas. After metadata is imported, it will be available as a version. Templates are an alternative way to reuse metadata. Templates can include both metadata, cell addresses, values, formulas and related metadata assignments. When a template is imported, the user can choose to apply just the metadata, apply assignments to existing cells, and/or include cell values and formulas. I will just briefly summarize the presentation so far, before I move on to show you the software. Research has shown that the majority of spreadsheets contain errors, and that users, even expert spreadsheet users, are not good at finding them. But as many as 75% of the errors are mechanical, which makes them susceptible to elimination. StrongTyping is a tool that can help spreadsheet model creators avoid these errors and, so, spend more time focusing on the business logic of the model. StrongTyping allows you to apply ideas from programming such as types, scopes and assertions, so that you are able to describe the purpose of the model more completely. Using this additional metadata, StrongTyping is able to identify those times when the formulas, and the cell references they contain, do not meet the additional specifications which are provided by the metadata. To find out more about StrongTyping, and to find out how you can create better spreadsheet models, contact us for a free trial. You will be able to use StrongTyping for up to 14 days. During that time you will have full access to training videos and be eligible for up to 2 hours free online support from a member of our consulting team to get you started. For more information, visit our website or email trial@strongtyping.com, or contact us by phone. Thanks for watching. We look forward to hearing from you. Lyquidity Solutions Limited is a privately held technology organization founded in 2000. We're experts in the use of Excel. Not just creating modules but creating whole reporting solutions using VSTO and other technologies. Our staff have created financial reporting systems for companies such as British Aerospace, Disney, Target and Dover Corporation. Since 2005 we have offered ComplyExcel. ComplyExcel is used by public companies, especially those which must be mindful of their corporate governance and compliance responsibilities. ComplyExcel provides the ability to monitor and control the use of Excel spreadsheets which are part of or contribute to the financial reporting supply chain. Currently ComplyExcel is used to manage and provide control to over 1 million spreadsheets. Our clients are across industry and organization types, and here is a sample. AMP Partners controls spreadsheets used to compute power rates to customers in Ohio. Asarco is an ore processing corporation based in Arizona. The company tracks changes to approximately 25,000 spreadsheets. At Cargill, ComplyExcel is used by the meat platform and the agribusiness to monitor approximately 10,000 spreadsheets, which include trading spreadsheets, many of which are changed throughout the day. DFAS is the accounting arm of the US DoD, which uses spreadsheets to check the numbers reported to the Congress. Grupo Mexico. Grupo Mexico is the largest mining corporation in Mexico and the third largest copper producer in the world. Belgian Fisheries
Use Comply Excel to monitor and provide control around spreadsheets used to report to the Belgian government and EU Commission.